So welcome to the second session in the morning. Quick reminder that immediately following this session, we're going to have a picture for snowmass taken outside, just outside the doors. So we need to stay on time because we paid for the drone to come at noon. This session will be moderated by, and the first talk will be by Ian Shipsey from Oxford University. So with no further ado, please go ahead.
Thank you very much. I hope you can hear me. Can you hear me? Great. If I get soft, please throw something, and I'm very responsive. So I'd like to welcome you all to the Enabling Energy Physics Research Summaries and Panel Discussion. I'll give a short introduction, followed by each of the frontiers giving their highlights, and then there'll be a discussion and questions. You'll save your questions for the discussion or use the Google Doc. So as you know, it has taken over a century to build the particle physics standard model and the corresponding cosmological standard model. These are true triumphs of our society, and they've been enabled fundamentally by looking at the world and using advanced instrumentation to do so. Our scope is extremely broad, and we develop many tools: theory, accelerators, non-accelerators, underground, astrophysical, and cosmological, advanced detectors, quantum, AI, machine learning, high-performance computing, and community engagement all play a critical role. We have, as a community, detected and measured over 24 orders of magnitude from the highest energy cosmic rays to the cosmic microwave background, and quantum sensing is extending that still further. We've developed an incredible range of technologies over the course of that time. And this culminated in the discovery of the Higgs boson in 2012 that enables us to exist, and to the observation of colliding black holes in 2016 by LIGO, a massive quantum detector. As Marcella said, there are many things missing in the standard model that we do not understand. BSM physics is at the core of everything that we do going forward. And there are therefore massive opportunities for discovery, but multiple theoretical solutions to all of these problems. And so experiment must guide the way. We are very much in a data-driven era, and we must continuously invent, reinvent, and make new tools. And when we do so, if history is any guide, this will be profound, because new directions in science are launched by new tools, much more often than they are by new concepts. The effect of a concept-driven revolution is to explain old things in new ways. The effect of a tool-driven revolution is to discover new things that have to be explained. And the fact that there are lots of unanswered questions inspires the next generation of scientists. You can see the fascination on the children in this control room at CERN. And they know that Galileo was right many years ago. We must measure what is measurable and make measurable what is not so. Now, between 1967 and 2012, we had a roadmap to guide us. The standard model guided our research, and it enabled us to have no-lose completion of the standard model. We had guaranteed discoveries. All the data we had pointed to the W, the Z, the top quark, and the Higgs before we discovered them. Now that the standard model is complete, there are no further no-lose theorems. In principle, the standard model can be valid to the Planck scale. And if so, much would be left unexplained, but there are no guaranteed discoveries. Some suggest that the universe is the way it is because if it was otherwise, we would not be here. The mass of the Higgs, the amount of dark energy, the values of other observables could be vacuum selection effects, a universe interpreted in terms of the multiverse, but it is premature to think so, because science progresses by experimentation, observation, and theory. Nobody would have predicted in 1850 that slight irregularities in blackbody radiation would have led to the entirely new conception of the world in terms of quantum theory, that we're now living in the second quantum revolution. That pondering the constancy of speed of light would have led to E equals mc squared, that special relativity and quantum mechanics would have led to antimatter. Experiments that explore uncharted territory or study phenomena we do not understand with great precision lead to a deeper understanding of nature. The Global High Energy Physics Program does that, Stress Global. The program will continue to reveal a cosmos more wonderful than we can possibly imagine. And to play a role in this journey of discovery is the aspiration of our field here and around the world. What we know is a droplet, what we don't know is an ocean. It's for us and the generations that follow us to explore it. When you have a roadmap, the way in which you approach data is very different to when you don't. the need for detail, the quality and quantity of the data depends on the distinctiveness of the object and the level of familiarity that you have with it. When you know the characteristics and the context of what to expect, for example, the W, the top, or the Higgs, a little data goes a long way. And top down, i.e. theory, dominates bottom up, which is data driven. I'd like to give you a visual example of this that you may have seen before. I want to show you an image. It's a partial image. It's not good detail, but it's of something, actually someone that you know very well. A former US president who died in the 1800s. And I'd like you to tell me what it is, because I've given you this data already. You're acting like someone that's theory driven. So who is this? Do you know? Put your hand up if you know. Call out the name. That's it, right? So you're theory driven. And so you managed to reconstruct Lincoln with very little data. And there he is in all his glory and wisdom. But now imagine that you don't have a roadmap, no theory to guide you, or many theories to guide you, and you don't know which one is right. Now look at the data, and I'm going to show you another image. I'm going to give you lots more pictures than I did for Lincoln, and ask you, do you recognize this image? What is this image? Very hard to recognize because you don't know any context, you don't have any theory to guide you, or you have multiple theories, you don't know which one is right. As we double the data, it's still difficult. As we double the data again, and double the data again, it's still difficult. In fact, we need a great deal of data before you see that this is Darley's brilliant, the persistence of memory. So with a roadmap theory, it's easy to find things. That's how we found the Higgs when the NHG turned on. It was relatively easy. But now, without a roadmap, you're data-driven, the new physics needs lots of data, and bottom-up, data-driven dominates. So we are in a data-driven era. And the other thing to say is that the detectors that we build have to be incredibly capable. And the reasons for this are shown here. This is a slide from Sam Ting. Facilities on the left, in the middle, the original purpose where these facilities were built. And now coming up in red is what they actually discovered. Evidence for the Z and the W before they were actually manufactured at the LHC, at SPPS. Two kinds of neutrinos, CP violation, charm, bottom, top, gluon, neutrino oscillations, and finally, the dark energy. None of these were anticipated by the experiments that performed the measurements, but the detector was precise. And because it is precise, that is the key to making a discovery when exploring new territory. Now, at SNOMAS, a long time ago, people trying to make predictions about the future. And this comes from 1982, when many of you weren't born and the rest of us weren't particle physicists yet. However, the prediction was that a primer on detectors in high energy luminosities environments, or why you can't do physics at 10 to the 33. But we did it. And that was just the beginning. Now we're doing it again with another large increase in luminosity, building the most capable detectors ever constructed. So the flagship program at the high energy frontier at the moment is the LHC and then the high luminosity LHC. It's a truly impressive and exciting program that I'm very confident will lead to interesting discoveries up to about 2040. And then going forward beyond that, the plans at CERN are for a big sister ambition, the Future Circular Collider, FCC-EE, in about 2040, followed by FCC-HH at a later time. And the evaluation of this will be in the next European strategy around 2026. So at the Accelerator Frontier, of course, there's also other alternatives, the ILC, CEPC, and a great deal of work is going on in the very exciting Muon Collider. Since 2013 at SNOMAS, there's been really dramatic progress in accelerator research. Very high gradients achieved in superconducting RF. Magnets are now being achieved at 14.5 Tesla in the US Magnet Development Program. Breakthroughs in plasma acceleration that relate to very high gradients over relatively short distances, and the observation of optical stochastic cooling with the outer ring at Fermilab, truly revolutionary achievement. At the same time, beams for society, all developed nations have accelerators. These accelerators change our lives and they help keep us safe. This is an X-ray source in Brazil, used in COVID virus studies and also for drug development, just like light sources around the world, but they come originally from our research and accelerators. And then there's the incredible miracle of flash therapy come out of the CLIC research program. And there is a research institute that should soon be delivering to patients in Lausanne. And also there's been work done in Cincinnati. In the instrumentation frontier, the biggest things that have happened since the last SNOMAS were first, the creation of the coordinating panel for advanced detectors. And that has enabled an annual instrumentation workshop proposed to the DPF the instrumentation prizes, which were adopted, the Graduate Instrumentation Research Awards and Graduate Fellowship with the DOE. We combine our advice on the SBIR, SJTR input program as requested by the DOE, and we have improved overall the coordination of US instrumentation. At the same time, there's been massive global collaborations that have led to remarkable results like Protege at CERN. The key technologies for the first student forward detector have been demonstrated. Look at the collisions at the LHC, and this is when the Higgs was discovered, 24 vertices. We know it's going to be 200 at the high luminosity LHC. We know that today, when we look at those collisions, it's like a fog, but thanks to LGADs, we're going to be able to see the physics in there very clearly in 4 dimensions. And those LGADs also are remarkably versatile, and there are many, many applications of them beginning to appear. We have the pleasure of having the electron-ion collider from around 2030 concurrent operation with a high luminosity LHC, which is spectacular for QCD. And we'll have a huge interest in the nuclear physics and particle physics communities in working together there. This is the approved detector, ECHI. And if you look inside the hood, what you see is that most of the technologies are exactly the same as for the high luminosity LHC and earlier accelerators like RIC. And nuclear physicists and particle physicists are working together side by side to achieve this. Since the last snowmass, there's also been the word quantum appear everywhere. Before then, it was not mentioned. That doesn't mean that there weren't quantum sensors before the last snowmass. However, we changed the name. We changed the focus. And the reasons we did this was because of the importance of quantum revolution 2 to society. The first quantum revolution was the exploitation of quantum additive devices, and we use them all around the world today. The second quantum revolution engineers large quantum systems with full control of the quantum state of the particles. For example, the iconic entanglement. And with an atomic clock, you can perform geodesy at 1 centimeter. With quantum annealers, you can analyze LHC collisions. With a very early IonQ 60 qubit, you could actually calculate with fairly high precision the chemical energies involved in chemical reactions and predict the behavior of catalysts. And then in 2019, Google achieved quantum supremacy. It's only the beginning of the quantum revolution, but it was an important demonstration that quantum computers are just very, very, very difficult to build rather than impossible. And so what that's meant for particle physics is that the technologies are in a new emerging area in our field. There are many different sensors and technologies being investigated. There are exciting programs at CERN, at DAISY, at Fermilab, and there are big programs funded by major agencies for the university community and national labs, for example, DOE's Quantized and UK's Quantum Technologies for Fundamental Physics, and there will be many more of these appearing. These bring new funding for high energy physics, as well as spectacular opportunities for interdisciplinary collaboration, which enriches us all. This is a plot of a possible dark matter mass, and what you're seeing in blue is where we search for the dark matter today. Either they're WIMPs or they're axions, the axions being very light, wave-like dark matter. With quantum technologies and the techniques shown here, we open up all of the light green space. So it's a dramatic transformation. Now, however, having said all of this, the last P5 recommendations, number 27 and 28, to support instrumentation and instrumentation in universities did not yet happen, and we need to do better. The future of software and computing fundamentally important for the way we do science, and it's changing the way we do science. AML is now widespread, but it was scarcely mentioned in 2013. Quantum computing is entering the stage with potential impact for quantum many-body systems, for event generators, data analysis, that is QCD, and so much more. At the same time, we say that software and computing are essential. But if we look at how complex they are, they're commensurate with the experimental instruments themselves, and yet they change on faster timescales than the facilities and the experiments. And so perhaps there's a need for an entity that can continuously promote, coordinate, and assist S&C, and perhaps CPAD for software and computing. Underground facilities have seen dramatic international breakthrough results in the since the last snowmass. These results are searches for dark matter, ever more sensitive. They're also the observation of the CO2 cycle in the sun and probing CP violation with neutrinos. Back in snowmass 2013, Dusan had been canceled. The future US underground science situation was very, very uncertain indeed. Now the situation is dramatically transformed. SERF is a world-leading multidisciplinary facility, hosted 2 generations of world-leading dark matter experiments. There's excavation ongoing for Dune and a haven for international underground science. in physics, biology, geology, and engineering. And when you look at the SNOMAS program that's developing here and what's being proposed, there's a strong case for the upgrade of this facility. Theory is fundamental, it's essential. There is no physics without theory and experiment. The US lags Europe in its support for the theory community. It is important to address this. Finally, our community engagement, interacting with connected communities, is fundamental to all of our well-being and our future. With the high energy physics community, with industry, with education, with policy, and with society. Back in SNOMAS 2013, the level of activity was shown by one bullet point, and look at the level of activity today. We have a much more ambitious community engagement program. And this will make HEP stronger and healthier and achieve the physics vision of SNOMAS 2021, at least, and help to define it itself. Remember that particle physics is global. The regions can together address the full breadth of our subject by hosting world-class facilities in each region and participating as strong partners in those facilities that are not in our region. Working together is the way we work in particle physics. That's a picture of CMS, 4,300 scientists and engineers and students working together. Our international collaborations inspire the public, they inspire the politicians, they inspire business. They're made up of an absolute myriad of individuals, each person playing a role similar to a violin in an orchestra. We all have a part to play. It's extremely ambitious. We are to achieve the vision for our field that we are united. I repeat, united in our aspirations. One field, one voice. Remember what Longfellow said many years ago, the only enemies you have are those you have not spoken to. Please speak to people if you disagree with their points of view and learn from them and listen to them if you're one of the people that is having that conversation. The SNOMAS process is wonderful for many reasons. And one is that it gives us a renewed and deeper appreciation of each other's science, as we saw in the wonderful talks in the first session this morning. Our science is compelling enough to compete favorably with the best talent in the world, where transformational and paradigm-altering advances are happening in other fields all the time. There is no entitlement to our funding, though, and we must compete favorably with other opportunities in other fields in the agencies, the NSF and the DOE. We must make the case in Congress. We must make the case in academia. When we discovered the Higgs, that's a victory for condensed matter physics, not just a victory for particle physics. And when we see our science as compelling, we need to convince others that's compelling as well. A healthy program needs a long-term strategy with a compelling vision for the future and future scientific achievements. And that is what I believe and what I am seeing SNOMAS 21 is producing, and hearing it through my cocktail implant as well. Great advances since 2013, and we are ready for the next P5. Thank you very much. Okay, so we're now moving to the panel, and the next speaker will be for the Accelerator panel, and Steve Gourley.
Okay, so let me get started here. We don't want to run over time. So there are three main components in enabling future accelerators. We look at the near to medium term future. And for this, we're proposing for the first time a National Future Collider R&D program, which I'll talk about in the next slide in detail. And then two other aspects for the medium and longer term. The General Accelerator R&D program that's been going on for quite a long time, and accelerator and test facilities to support that. All right, so one of our messages on colliders is that we need an integrated future collider R&D program to be able to engage in the design and to coordinate the development of the next generation collider projects. This would address in an integrated fashion the technical challenges of many promising future collider concepts that we've seen in the last 8 days that are not covered by the existing GUARD program. And they would also enable synergistic US engagement in ongoing global efforts like the FCC, the ILC, and the International Muon Collider collaboration, which we have not been able to participate in. And then, more importantly to us anyway, is to develop collider concepts and proposals for options that are feasible to be hosted in the US, for example, C-Cubed, Helen, Muon Collider, and so on. On R&D, we have an ongoing R&D program that's aimed at fundamental beam physics and long-term accelerator concepts and technologies, RF, magnets, beam physics, advanced concepts, targets, and sources. All of these, as we've seen, have very broad applicability across future accelerators, taking ideas generated by the universities and laboratories to a different level. And we all know, I think, understand that R&D is key to enabling facilities for future machines dealing with neutrinos, rare processes, and colliders. Oh, this thing didn't, okay, this didn't work. Okay, so we have, these are essentially the GUARD areas. So we have sources and multi-megawatt targets. Now this was added after the last P5, in fact, after the sub-panel that followed P5. This was added to the GUARD portfolio. So we're looking at next decade. So some of these are ongoing, some of them will depend on P5's priorities. So we have, on this side, we have intense E+ sources. This is something that every E+ minus collider needs. A possible 2.4 megawatt upgrade for PIP3, and then for the Muon collider, 4 to 8 megawatts. The magnet program, the US Magnet Development Program was another outcome of the Accelerator R&D subpanel. It integrated the 3 laboratories that were working on magnets in the US, Brookhaven, Berkeley, Fermilab. It also includes the National High Magnetic Field Lab in Florida State University that does a lot of materials research that supports this program. And right now, 16 Tesla dipoles is one of the 4 focus areas, niobium 310 dipoles, along with HDS, technology development, and general materials development. And in the future, that could be expanded to look at 40 Tesla solenoids for a Muon collider and very fast ramping magnets for several applications, including Muon collider. And then the other thing that happened in the ARD subpanel was that we combined superconducting and normal conducting RF into one thrust area. They'll be looking at 70 to 120 megavolt per meter structures for C-Cubed, traveling wave option that would be the basis of Helen, new materials, and then high Q and efficient RF sources, which are hand in hand with energy reduction, and also that's a very important aspect of cost reduction as well. So it's a win-win in that situation. And in Wakefield's, they'll be looking at collider quality beams, efficient drivers and staging, and close collaboration with the international community. And then tying all of this together is Accelerator and beam physics, where they try to understand high intensity, high brightness beams, acceleration and control, incorporate high performance computer modeling and AI ML approaches. AI and ML seems to be a common thread in everything we've been talking about this last several days. And then design integration and optimization, including energy efficiency. All right, so coming to accelerator and test facilities, this is how we develop these technologies. So we have superconducting RF and superconducting magnet tests going on in these laboratories, beam physics facilities at Fermilab, Brookhaven, and Argonne. You heard about IOTA, and then the Wakefield plasma studies going on here. What we're missing right now is a facility for multi-megawatt beam targeting R&D and testing. Now, when targets and sources were added to GUARD, the expectation was that there would be money coming with it. I think they were an order of magnitude less than what they were hoping for in that area. So that's something that needs to be beefed up a bit. And also over here in superconducting RF, or just RF in general, I should say, there's a need to upgrade some of the facilities, augment them, modify them so that they can explore some of these new materials and ideas that they have for improving RF efficiency and gradient. So that's it, but I want to add one thing just to sum it up in a very, very simple way. You guys decide what you want to do. Tell us, easy. We're going to take the easy part, okay? You decide what you want to do. Give us the flexibility and the resources, and we'll figure out how to do it, okay? It's easy.
So the next speaker will be remote. Reese Quinn.
Yeah, I need to let you, need you to let me share screen. Yeah.
You should be able to share your screen.
Okay, just a moment. And there we go. Okay, we good? Everything okay?
Yep.
Okay, great. Well, good morning. So what do we need to do in the community engagement frontier to really move forward our field of high energy physics and achieve the vision that we're trying to develop now? Well, first I want to bring back a graphic that Katevi showed earlier in the workshop. And that is that among all of the frontiers, community engagement frontier is the one that all of us felt the least informed about the direction of. And so, you know, how do we do addressing that during this past week or so? Well, this is sort of how folks responded to the opportunities to learn more. This was a picture of our only community engagement frontier parallel session that was sort of open to other folks other than just a topical group convener working meeting. In fact, this was a cross-frontier session specifically covering all the frontiers. And so this was the attendance. Most of the people in that picture are actually CEF topical group conveners. 5 frontiers sent no representation at all to this. Now, we do recognize, though, there were lots of other parallel sessions going on in the other frontiers that were very important. But, you know, there were lots of other cross-frontier sessions last week. I don't think most of them were this sparsely attended. And also, low attendance was pretty similar in our plenary and lunch sessions, most of those, regardless of when they were scheduled, without competing sessions. But we do absolutely recognize that there are legitimate and really understandable reasons for this, not just for the past week, but for the whole 2 years of SNOMAS, this low participation, real reasons that are structural related to how we've organized SNOMAS, and then also very serious concerns about career advancement and how participation would affect that. And so there's absolutely no blame or recrimination, but we do need to acknowledge this, and that, you know, this work over the last 2 years was really put on just a very small number of your colleagues, really to the detriment of their careers in many ways, including the fact that they were very limited in their ability to participate in the other physics frontiers through SNOMAS. And so we need to look at this and to address it. Perhaps that means that SNOMAS is not the best time to focus on this development work. And that's what the frontier is really about, is not just engaging in community engagement, but doing the development work to expand and focus it to move our field forward and achieve our vision. So I want to address this 98% that would like to know a little bit more about what we've been up to the last couple of years and where we're going. I'll do that group by group. Environmental and societal impacts. 2 big major goals here: minimize our environmental impacts of our activities and maximize the quality of our local community relationships. There are specific areas where we could use some resource support here, particularly in the area of climate change mitigation. We need to, you know, develop reduction goals and reporting to be comprehensive and standardized across all our facilities. We also need to invest in energy-saving technologies in very timely deploying the next-gen remote meeting tools for that to help. In public policy and government engagement, we've done, a lot of really great work in this over the last several years, particularly since the last P5, with great results for funding. But we need to expand that funding advocacy, particularly to more in the executive branch, local and state governments. We also want to partner with broader science organizations to be really effective in our advocacy for non-funding issues as well. Specific areas that we could use targeted support. The technical and logistical tools to carry out the level of advocacy we do. It's a pretty large job that's done on a volunteer basis. It needs to be more sustainable. And we need to expand our training programs, enhance them, and make them available to more than just the folks that are going on the DC trips. Public education and outreach. A lot of people are involved in public engagement and doing really great work in that. But there are sometimes costs to doing that and barriers. And so we need to change the structure to enable that better. And also, whatever communities or audiences we're trying to engage with, we need to really build relationships and partnerships with them and not just talk to them. And so largely that depends on developing and putting into practice training programs very broadly in science communication, specifically targeted in creating communication plans in partnership with your audiences. And then, these barriers and lack of rewards for doing this work, there needs to be a structure of rewards and benefit to people for doing this. I love my little statue I got from the last Snowmass, but we're really talking about things that are a little bit more concrete, significant, and meaningful to people's careers here. Physics education. We know that it's very effective in nurturing student interest in science if you have partnerships between universities and local K through 12 educators and students. We want to build on that. We need to enhance our degree programs that will be better fits to the careers that people are heading into now. And a big thing is that we need to grow our participation in our field from our non-R1 colleagues, from primarily undergraduate institutions, community colleges, and also expand our international student collaborations. Resources would be very much needed for things like dedicated grant support for master's students. We're envisioning a different kind of career path for master's programs. And also what would be of great help for our PUI and CC faculty is the availability of teaching buyouts. DEI we've heard quite a bit about over the last week or so. There are big goals here to really re-envision our workplace norms to address these community-related issues we've heard a lot about in different panels. Also, we need new ways of organizing ourselves and doing our decision-making that really gives agency and leadership to all of our stakeholder groups. And then very important is we need to bring in outside experts to partner with us with their expertise in many different disciplines to move this work forward. That involves, creating pathways for people from marginalized backgrounds to support their careers in different ways. And also it's going to take money to bring in these outside experts. So resources have got to be found for that. Career pipeline and development. Again, a big focus for this group was non-R1 academic colleagues, getting them more involved in HEP, but also getting more educational and career opportunities for students in engineering and industry-focused research. A big way that we think that we could develop that is by really developing alumni networking, developing a portal to maintain these connections with colleagues that we have that are now in industry. Also, those buyouts would be important here, and training programs in career skills, preparing people for other careers. Then applications in industry. Again, engineering departments are going to be important here to create technology-focused education and specifically application-driven research opportunities. Also, we need new policies and programs across agencies, specifically for technology development that is focused on technology goals rather than science goals to get cross-agency synergy, and also technology transfer leading to commercialization. We need to partner with early stage scale-up companies on specific projects, and again, updating policies directed at specific technologies to advance them. A couple of specific areas: making public-private partnerships between our different communities for accelerating lab-to-fab innovation, for example, on heterogeneous integration, and prioritizing and simplifying how our industry partners can access our resources for things like flash radiation therapy that was mentioned earlier. There are some frontier-wide goals. Our two big goals in SNOMAS frontier-wide are this. It is really important that all of us agree that everyone's got to work together on this CEF work to organize and develop our community engagement efforts really in a coherent manner that's going to be focused on strengthening our HEP community and helping to achieve the vision that we're developing. So that's what CEF is about, and we need to work together on that. To do that, we're going to need to develop a structure or framework within our community to take ownership and responsibility of two things: implementing the CEF recommendations and monitoring their progress across the entire field. Previous SNOMAS recommendations in communication, education, outreach, some individuals moved some of that forward, but as a whole, it didn't really move very far. What that means is all the stakeholders are going to need to form some kind of P5 equivalent to shepherd these recommendations. That group's got to have direct connection to multiple streams of resources. This is as opposed to P5, which is a creature of the agencies, right? Because the agencies are the ones that fund and implement our projects, so P5 lives within that. But this is going to need to be much broader. I mean, there are some things that the agencies by law can't provide resources for here. And also how we integrate CEF into SNOMAS. Maybe we need to do the major CEF planning work asynchronously to not be in competition with the physics frontiers for time that we can devote to it, while the other frontiers could still report on activities and have that be a part of their SNOMAS activities. And then the frontier-wide areas that we need support for. For this structure that we develop, it's going to have to be staffed. We need administrative staffing to help with this implementation and monitoring. Surveys, research needs to be done on existing work, and those take money, they take time and effort. The tools and rubrics to monitor and evaluate are sometimes more complex and harder to develop. And really important is somehow structurally, we've got to find tangible support for all of our researchers and colleagues to participate in all these different areas of community engagement, in grants, hiring, performance reviews, all of that. And so these are the things we think we need to do, over the next few years to really move our HEP vision forward. Thanks.
Thank you, Bruce. The next speaker is Daniel Elvira. He will also be remote, and he will be representing computing and software.
Okay, so in the context of enabling the physics goals, I will give the summary for the computational frontier. And I will do this on behalf of my two co-conveners, Stephen Gottlieb and Ben Nachman, our topical group conveners, and all the contributors to the, I'm not sharing.
Do you want to share your slides, or you want us to put them up?
Yes.
What, you want us to put them up, or you're sharing?
I'm sharing. Can you see them?
We're seeing your login screen for Mattermost.
Okay. Now you see them, right?
Yes, we can see them.
Okay, I am very sorry for that. So I will give, in the context of enabling the physics goals, I will give this presentation on behalf for the Computational Frontier, and I will do that on behalf of my two co-conveners, Stephen Gottlieb and Ben Nachman, and our topical group conveners who have done a really great job, and all of the contributors to the Computational Frontier SNOMAS effort. And first, I would like to share with you an important disclaimer. The fact that the content of these slides still do not fully reflect discussions and comments that we have received during the CSS. But you can find pre-CSS versions of all the topical group reports and also the overall Computational Frontier report if you visit our Wiki page and scroll down under draft reports. As you can imagine, we are receiving a lot of comments from many sources, and we are really working hard. We are doing everything humanly possible to implement them in a consistent way, but you understand that this is going to take a few more days. So in the meantime, we would like to invite you guys to submit as many comments as you want, and you can do that using the document, the Google Doc that you can see here in this slide. So now let me share with you a few notes about the time frame for the report and also a couple of distinctive features of computing. SNOMAS is about the future, and all of the attendees know that people have been talking about future facilities, and that refers to the post-2035 period. But the truth of the matter is that the near-term program before 2035 is not really a given, and we must all make a strong case for it. And in fact, the Computational Frontier has received advice to focus on the upcoming 10 to 15 years in this process. And there are good reasons for that. One of them is that we need to secure funding to bridge a gap between needs and resources of near future programs. The other one is that computing technologies evolve very quickly, and it's difficult to make predictions beyond 2035. Projections will be very accurate. With respect to the distinctive features of computing, let me mention that, as I actually said before, computing technology and software paradigms change on a much faster scale than the life of particle physics experiments, and many software and computing efforts are neither funded nor managed as projects, which is the case for facilities and experimental devices. So we thought, how can we actually start the process of writing the Computational Frontier report? And one idea was to actually reread the P5 report that was issued in 2014. And if you go to page 21, you will find recommendation 29, and I would like to read it for you. Strengthen the global cooperation among laboratories and universities to address computing and scientific software needs, and provide efficient training in next generation hardware and data science software relevant to particle physics. Investigate models for the development and maintenance of major software within and across research areas, including long-term data and software preservation. So you note that these are really excellent recommendations, and they are very current. But action is still pending to a large degree on many of these areas. The 2014 P5 report also contained two paragraphs, I believe in page 46, on computing as a science driver. And what they do there is to talk about the past initially, mentioning that HEP played a leading role in high throughput distributed and grid computing, online data processing, high performance computing and networking, large scale storage, and World Wide Web. They also mentioned that the HEP community successfully managed software development and operations on a global scale. And they also talk about the future, which is, by the way, now the past, and highlight high-performance computing, large data sets and complexity of the data and the detectors, as well as the need of higher fidelity theoretical calculations and simulation in general. So what happened after 8 years? Where are we now? And the fact is that many of the statements would be the same. We are still handling large data volumes, detector complexity increases, we need more precision. And it is actually more true than ever that software and computing is a global endeavor, and efforts should be coordinated with worldwide partners. But something that is not emphasized enough is the fact that size and complexity of the software and computing effort is commensurable with that of the experimental instruments. And for example, we would benefit from making detector software part of the detector project from inception at the time when we are designing the detector. And that would have a tremendous impact, for example, on the performance of the reconstruction algorithms. But certainly the highlight, what should be emphasized very strongly in our report, and it will be, and should actually make it in the P5 report, is the fact that software and computing technologies are changing the face of energy physics, and they are actually changing radically the way we actually do physics analysis. And there is a trend towards computing hardware heterogeneity and specialization that is irreversible, and increased use of high-performance computing facilities. When we talk about artificial intelligence and machine learning, you have to realize that it was not even the horizon in 2013, and deep learning changed things very radically. And we cannot even talk about machine learning as an emerging technology because it's widespread, it's all over the place in every area. The emerging technology that is coming strong is quantum computing. It's entering the stage with a potential impact on quantum many-body systems, event generators, data analysis, etc. So we have a main recommendation. We recommend the creation of a standing coordinating panel for software and computing, CPSC, although of course we can discuss the acronym, under the auspices of TPF, mirroring the panel for advanced detectors, CPAD, established in 2012. This panel was mentioned by Ian in his introductory presentation. And of course, we should spend the next few weeks and maybe months discussing the scope and the charge for this panel if we decide to create it. But let us try now a first draft and read it to you. Promote, coordinate, and assist the HEP community on software and computing, working with scientific collaborators, grassroots organizations, institutes and centers, community leaders, and funding agencies on the evolving HEP software and computing needs of experimental, observational, and theoretical aspects of the HEP programs. The scope should include research, development, maintenance, and user support. And let me tell you what this panel would not be. It would not be an institute, it would not be a center, and it would not manage a budget. In addition to this main recommendation, we have identified critical challenges, or, we can call them findings, that are limiting the physics output of the US HEP community, and this include, let me go to the first finding. Long-term development, maintenance, and user support of essential software packages cutting across project or discipline boundaries is largely unsupported. And we all know that grants these days typically fund groundbreaking research and development, but not so much modernization, maintenance, and user support. And there are many examples we can give in the area of event generators or detector simulations, such as the GM4 toolkit. The recommendation is therefore that the US HEP community takes a leading role in long-term development, maintenance, and user support of essential software packages with targeted investment. Finding number 2 says research and development for software and computing cutting across projects or discipline boundaries receive insufficient support. Once again, there are examples that include the software and computing aspects of theoretical calculations, generators, cosmological, accelerator and detector modeling, machine learning methodology, and hardware ecosystems. This is a very important topic, algorithms, etc. And the recommendation is that through existing and reshaped funding programs, cross-cutting R&D efforts should be supported for proof of concepts to prototyping and, if successful, to production-ready deliverables. So let me recap. Finding number one had to do with maintenance and user support. Finding number two has to do with research and development. And the challenge number three says that scarcity of personnel and expertise jeopardizes the ability for full and optimal use of heterogeneous and high-performance computing resources. And we have to observe that it's really difficult to put software, given that we are actually trying to use so many different hardware platforms. And we also have to remember that some of the algorithms we work with are not suitable for parallelization and will require the survival of traditional CPU-based computer, at least for the next few years. And the recommendation is that we should support computing professionals and researchers and physicists for code re-engineering and adaptation to use heterogeneous resources effectively and to serve the needs of inherently serial algorithms. Traditional CPU-based hardware should coexist with the heterogeneous resources. Let's go to the last of our findings. Investment in training and career paths with help for software and computing researchers is insufficient. And our young people know too well that faculty and staff positions in software and computing for help are scarce, and therefore there are shortfalls in expertise, and this has become endemic. And the recommendation is that documentation and training efforts at multiple levels should be encouraged and extended. To enhance their career opportunities, bridge positions and awards should be created for help scientists and engineers working on software and computing. And we will explain in detail what we mean by bridge positions, because there has been significant confusion about this. We will explain this in our report. But before going to the final slide, I have to say that there is another very important topic related to number 4 that has to do that through the process, NOMAS process, we have identified issues related to diversity, participation, and climate within the software and computing community. And this will be discussed and addressed prominently in our report. We haven't actually written a recommendation in here because we are working on this, and we don't want to just say that we need to create or favor a diverse workforce. So to finalize, unsurprisingly, the recommendations of the Computational Frontier resonate with the European strategy, which is spelled out in this recent report, and invite you to read these quotes that we have extracted from their documents. Thank you very much.
Thank you very much, Daniel. The next speaker is Petra Mikhail, who will represent the Instrumentation Frontier, and she is live, not virtual.
Caption the top right. No. Okay, maybe I can start, if you can hear me. Okay, so these are the findings from the Instrumentation Frontier. I would like to thank my co-conveners Phil Barbeau from Duke and Jinlong Zhang from Argonne, and all our topical group conveners. We had 10 topical groups, and top right, please. That did an amazing amount of work, sifting through hundreds of LOIs, white papers, organizing working group meetings, workshops, and eventually solicited white papers. And basically, out of all those, it was obvious that we have an enormous amount of amazing technology that has been developed, is currently being developed. And we have a lot of ideas of where we need to push our technologies in order to enable the physics of the future. However, there's a big problem, and that's what I would like to focus on in this talk. So today's IF key messages that we have developed here at SNOMAS are almost identical to those from 2013. Although personally, I looked at them 2 years ago at the beginning of this, I did not look back at them over the last 2 years, and we came still out independently with almost the exact same messages. Last time we were recommendations 27 and 28 out of 29. And just to remind everybody, so the science frontiers physics goals will not reach their maximum potential if the community and P5 do not support detector instrumentation in much stronger terms than they have done over the last decade. And just to point out, obviously, IF advances relate to all the P5 science drivers. All right, so diving straight into our 5 key messages. Number 1, and it turned out the other 4 pretty much boil down to this one, so we would like to start with this one. We are recommending to double the US detector R&D budget over the next 5 years and modify existing funding models to enable R&D consortia along critical key technologies for the planned long-term science projects, sustaining the support for such collaborations for the needed duration and scale. Since the last SNOMAS, funding for detector R&D in the US has been on the decline. Detector R&D shares the same pot of money, at least on the DOE side, with detector facility operations, which need to be protected at all costs. Any decline in research funds for detectors has a direct hit on the R&D component. CERN R&D collaborations for targeted and coordinated detector R&D were widely successful. We recommend the establishment of a similar model of R&D consortia in the US along strategic technological directions and perhaps under the guidance of CPAD. We recommend a strong link to the newly formed R&D collaboration model at CERN following the ECFA roadmap. Key message number 2, we would like to advance the performance limit of existing technologies and push new techniques and materials, nurture enabling technologies for new physics, and scale new sensors and readout electronics to large integrated systems using co-design methods. The detector R&D community in the US is doing amazing things. We are at the forefront of pushing old technologies into new territories and of inventing new detectors and methods to enable breakthroughs in many areas of science. In order to support the key science goals, the overall HEP community needs to get behind the detector instrumentation experts and help them achieve these technological feats going forward. We need you to help us get increased funding, a sustained and valued workforce, and world-class facilities so that we can build the detectors of your dreams. Message number 3, develop and maintain the critical and diverse technical workforce and enable careers for technicians, engineers, and scientists across disciplines working in HEP instrumentation at laboratories and universities alike. We need training opportunities for PhD students, including interdisciplinary studies and pure instrumentation PhDs. These need to be followed by a realistic and sustainable career path in instrumentation, both at the laboratories and universities. We need to nurture our technical workforce of highly specialized technicians, engineers, and scientists from other disciplines, such as chemists, material science, biology, nanoscience, etc. These skills cannot be found on the street and take a long time to train and develop. We cannot build these amazing HEP detectors without our technical workforce and without giving equal value to colleagues working in instrumentation. Number 4, expand and sustain support for blue sky, tabletop R&D, and seed funding. Establish a separate review process for such Pathfinder R&D. HEP needs both evolutionary and revolutionary progress. Evolutionary R&D pushes existing technologies to their achievable limits for low risk and a known reward. Revolutionary R&D, also known as blue sky, is of high risk and potentially high reward, pursuing completely new ideas with uncertain outcomes. Blue sky R&D often leads to null results, but sometimes has the ability to open completely new realms of sensitivity or even new fields of science. We need a balance of both kinds of R&D. Evolutionary R&D can address immediate science needs, such as the next Higgs factory, while revolutionary blue sky R&D is needed to even get anywhere near what we need in the long-term future, such as an FCCHH detector. Both streams of R&D are not easily compared with each other. We recommend to create a separate review process for blue sky R&D and to reserve a certain fraction of the R&D budget for the most promising ideas. And last but not least, number 5, we need to develop and maintain the critical facilities, centers, and capabilities for the sharing of common knowledge and tools, as well as develop and maintain close connections with international technology roadmaps, other disciplines, and industry. The detector facilities in the US are at the heart of our field. Without them, we would not be able to build the detectors that deliver our world-class science data to us. Such facilities are expensive to maintain and to upgrade to the state of the art. Similarly, the tools and methods we need to develop our detectors, including design and simulation software and licenses, need to be maintained and shared among institutes. It is essential that we seek close collaboration with national and international partners in HEP and other disciplines, as well as with industry, in order to profit from the latest advancements in material science, or to bring new technologies to cost-effective mass production. And then I just wanted to briefly flash through and show you that instead of just complaining and begging for your help, we do an enormous amount of amazing things. So these are just some recent examples: enabling science for neutrinos and rare precision physics, for astroparticle physics, and for collider physics. And with that, I would like to conclude that the community really needs to rally behind its detector colleagues, but won't have the detectors it needs to achieve its science breakthroughs in the future.
Thank you very much, Petra. Next up is Nathaniel Craig, who will represent theory.
All right, thank you very much. So it's a great pleasure to be part of this panel on enabling the physics goals on behalf of the Theory Frontier, again, alongside my co-conveners, Chapa Chaki and Aida Al-Qadra, really reflecting all of the work that's gone in the Theory Frontier from our topical group conveners and from the many contributors and liaisons. I should say both the goals that I'll talk about today, right now, and also many of the science highlights that Aida talked about earlier this morning are present in our Frontier and topical group summaries, which you can get to here. And if you wish to provide any feedback on those summaries, you can also do so. We have a dedicated Google Doc. So if there's anything that I mentioned in this talk or anything that came in Aida's talk, I would really encourage you to take a look in greater detail in the documents. So, there's sort of two parts to this panel. There's goals and there's critical needs. And so, what are the goals of the Theory Frontier? And in fact, why is the Theory Frontier appearing in the enabling science part of the panel this morning? So broadly, the goals of the Theory Frontier, I think the goal, which connect to the goals of HEP more broadly, are to advance our understanding of nature by pursuing a very broad and balanced program of theoretical research that covers the entire spectrum of particle physics. As Aida's articulated, that fits into fundamental phenomenological and computational theory. But really where it comes in particularly to the enabling science part is the connections, is the sense in which theory can serve as a glue for the HEP enterprise. And so a main goal then is connecting the frontiers of particle physics, in particular, enabling the comparison of data across different scales. And if I can respectfully disagree with our August moderator, sorry, Ian, I actually don't see really in the modern era there being data-driven and theory-driven eras. I think in a healthy scientific ecosystem, they are deeply and inextricably intertwined. What does change, what does evolve is exactly how those two intertwine. And I think what's been interesting to see evolve over the last 2 decades is particularly in the role of theory away from sort of a strictly prescriptive direction into a much more interactive direction in which it helps experiment to not just interpret the data, but to relate data between different experiments at different scales, to identify new directions for inquiry, and to fit them all into a bigger picture. So I think the way in which the relationship has evolved is very rich and exciting, and that's what has made this SNOMAS process in particular, I think, really thrilling. So in addition to relating experiments in the different frontiers in a coherent picture, the idea is also to explore new directions and also to bring things in from the outside of HEP, incorporate new developments from other fields, and build bridges, gravity, cosmology, astrophysics, quantum information, nuclear physics, AMO, condensed matter, and even disciplines outside of physics, statistics, computer science, data science, and mathematics. So our goals, particularly as they relate to experiment, of course, are to fulfill the theory needs of current and planned experiments, right? To allow the data to be interpreted and also just the motivation of the experiments themselves. And in some parts, of course, analysis of the data. But also to be responsive to the results, right? I think we've seen, particularly in the last decade since the last snowmass process, the results from experiment really are shaping the directions that theory is pursuing. Of course, looking to the further future, the role of theory is to envision and motivate future experiments and to furnish the tools necessary for the success and the successful interpretation of that data. But I just also want to emphasize, of course, the role of theory is very strongly connected to experiment, but it also has a component that is the pursuit of exploratory research. And that is because all of the things that we do now, whether they be experiment or more phenomenological theory, they started out as some form of exploratory research. And so it's important, of course, that we commit to that and invest in it as robustly as we can. Of course, there's also aspects of the community that are major goals. So one very important aspect is we have US leadership in the international theory community. That has been a very great historical strength of HEP in the United States. And that is something that I think we would very much like to sustain because that sort of leadership is invaluable. I also want to echo something that I think Jesse Thaler put very nicely in his plenary talk a little bit earlier in the program, which is that, we'd like to cultivate a vibrant, inclusive, and supportive scientific community, and very much embedded in the language of HEP. That means developing 4-pi coverage in identifying and fostering talent at all career stages. Of course, also in the spirit of workforce development, we really need to maintain theory as part of HEP, the program that trains students and junior scientists, giving them both physics opportunities to actually allow them to contribute to science and also preparing them for their future in whatever endeavors they undertake. So what are the critical needs? These are the goals, I think, of theory, also more broadly, many aspects of HEP. So what are the critical needs that we'd really like to satisfy in order to achieve those goals? So I think the central one is support for the essential role of theory that is very much analogous to what we've already seen articulated in the European strategy update. So our colleagues in Europe have done, I think, a beautiful job of articulating the essential role of theory, both in relation to projects, but also in its own right. And so I won't read to you this beautiful paragraph that appears in the European strategy update, but I would encourage you to take a look at it. It appears very prominently in the strategy update, and I think this is a real template or model for ways to talk about theory as it relates to the HEP enterprise. But we also have 3 more things I think that are necessarily critical needs. So very broadly, this isn't just a point about theory, this is, I think, a point broadly for the community, is the need for support for a balanced program of projects and research. Because as we've seen throughout the snowmass process, both of them are essential to the health of the field. And that's reflected in part by Jesse's modification of the P5 science drivers with the role of R&D and other critical infrastructure in the center, as well as the sort of 4-pi coverage around the outside. So on the spirit of the 4-pi coverage, another critical need is support for people, right? Especially early career, and that is support in every sense of the word. And that's because, you could ask, what is the infrastructure for research? A prime infrastructure for research are the people. And so to the extent that research is essential to our endeavor, the infrastructural support for people is also essential. And then finally, relevant to theory, but also more broadly relevant to the research endeavor, is support for targeted funding that advances the physics goals. So we have a lot of present and past examples of bridges that help, in particular, at the interface between theory and experiment, that can necessarily strengthen relationships that the resources in either part alone are not necessarily adequate to do. So there are a lot of good past examples, present examples, future examples that we've heard a lot about during the snowmass process. These are essential. They should not, of course, replace the broad research mission, but to the extent that they can augment it, they play a vital role. Okay. So you'll notice that in all of these critical needs, they've all started with the word support. And so if I can just say one thing to conclude, it's that although, of course, we divide up all of our physics by frontiers as an organizational method in the enterprise of snowmass, we are all part of one HEP community, one scientific endeavor. And it is the support for each other and the support for each other's science goals and career goals that are really going to allow us to achieve all of our greatest dreams. So thanks very much.
Thank you very much, Nathaniel. The next speaker is Jetta Hall. He's the last speaker before the panel, and he'll be representing the Underground Facilities Frontier.
Okay, thank you so much. Weighing in on the controversy of this panel as to whether or not data-driven or theory-driven is the right way to go. I think, the discovery of the positron is a beautiful model, and I think the discovery of the muon is also another beautiful model. And in the end, I agree, it's all just interconnected across all these frontiers from what we're seeing. I wanted to thank my co-conveners. I think particularly for us in underground facilities and infrastructure, SNOMAS has been a catalyst for a lot of very good discussion amongst us and settling a number of issues that we've had throughout this process. I wanted to thank the conveners, the organizers, and the community for showing up. This process has been enormously valuable. I just wanted to show some of our goals from the beginning of SNOMAS to show you, the simple roadmap we had, but the difficulty that we have, which is really just to look at what exists in underground facilities and infrastructure, look at the supply of these things for the community, and then ask you what you need for your scientific goals. What is the demand? And then compare those. It's simple to say, but this is obviously a tricky thing to do. And it's been really important to be at SNOMAS and be embedded in these discussions as the scientific goals get refined and those messages really come to light. In the end, we'd like to generate a recommendation for a bold integrated strategy for underground facilities and infrastructure. Just drawing some of the threads to the science and to the last SNOMAS is something I'd like to do in this talk. I did want to make the point that looking back to SNOMAS 2013, which I did participate in, there's been extraordinary progress. I really wanted to highlight, given the recent results from LZ, that the G2 dark matter direct detection program is nearing successful completion. Those detectors are being deployed, and now we're in the phase of really getting to operations and then final scientific production and hopefully a discovery. Underground neutrino physics has delivered and is poised for more discovery. I think that's clear from the excitement in the neutrino frontier. And supporting capabilities in the underground facilities and infrastructure, for example, material assay, safety, operations of these large cryogenic experiments, they've all successfully scaled up to the requirements of the ambitious SNOMAS program that was identified last process. Just a few notes about the long baseline neutrino facility. This is really world-class underground infrastructure, both at Fermilab and at the far site in South Dakota. LBNF enables US science priorities and accelerator-based neutrino experiments. And there's a lot of interest in a lot of the other physics as well that can be done with these detectors and with this facility. R&D, one place where we see there could be a need for underground facilities and infrastructure, both at say Fermilab and potentially in South Dakota, is the research and development over the next decade for say the module of opportunity in Dune. Did want to point out that construction is coming along quite well. This is a picture from about a month ago. All the drifts now exist for the long baseline neutrino facility. This is one of the detector halls. I can't remember if this is north or south, but it is at full width now in this part of the drift, and they're just finishing moving that through the rest of the drift and then going a bit deeper. So they're well advanced and they're making impressive progress. Other neutrinos and rare processes are included in the scientific goals. I took this plot from Kate Schulberg's summary talk, which came from this archive paper. And you can see the enormous number of experiments and enormous number of technologies if you look at her talk in terms of what's needed. And many of these, especially down at the lower energies, require underground infrastructure. And we're not counting the underwater infrastructure or even the atmospheric monitoring infrastructure for some of these higher energy experiments. One thing that, in the neutrino frontier and in the rare processes frontier, we've seen double beta decay show up. This is also a compelling experiment that addresses a number of neutrino questions. And it will require large facilities for the ton scale. And you can see beyond ton scale, targeting the normal ordering showing up in this SNOMAS. And I would say, one of the requests we have from underground facilities to the Neutrino community, thank you, is that we have the depth requirements for these beyond ton scale targets, because advanced planning is required for the development of the underground infrastructure. And we don't want to build infrastructure for this double beta decay program that doesn't fully address the physics goal. And the cosmic frontier, we see substantial underground infrastructure requirements. I took this plot, this beautiful plot from the cosmic frontier and from the summary talk by Aaron Chu. I also wanted to call out the Paths 2 talks from some of our colleagues, Tracy Slatyer, Kyle Dawson, Risa Wexler. They demonstrated the exciting and complementary discovery spaces accessible over the next decade of cosmic frontier research. And we see a number of requirements for underground facilities and infrastructure, including next generation dark matter searches up here at high energy, at low energy, and also R&D for next generation devices and projects will require some unique underground infrastructure. We are certainly in underground facilities, we're important for delving deep, and we see a role in searching wide. However, we tend to aim low in our particular frontier. On the other side, we also need clean, radon-free space and more sensitive assay for future projects. Some of the double beta decay and dark matter goals require larger clean rooms now with lower radon levels than currently exist, so that is a clear need. Radon is increasingly a background for a number of experiments, and we need increased monitoring and measurement techniques for those. And then one interesting note is on the high purity germanium. So for high volume screening, we do believe that most assay needs will be met by existing facilities that have ramped up over the past decade, but we do require organized cooperation between facilities and experiments to utilize that in the most efficient way. On the synergies, there, underground infrastructure is clearly a rising tide that lifts many boats. One thing that we really want to point out is the synergy between dark matter requirements and quantum science and technology advancements. So I took this summary slide from Aaron Chu looking at QST, HEP intersections. And in his title, that says it all. Qubits are detectors. And in terms of underground infrastructure, his slide also points out we're providing HEP instrumentation and low background underground test stands to make more robust qubits and better dark matter detectors, so you can see the synergy. There are a number of other applications, engineering, including geothermal energy, underground operations, access to ancient water, for example, underground, facilitates unique geology studies and biology studies. There's a tie-in to nuclear non-proliferation and others. Underground accelerator-based nuclear astrophysics, for example. Okay, so here is probably our highest priority ask. This is the bold vision that we would like to get out to the community. So really, hopefully I've explained that the ambitious vision requires additional underground facilities and infrastructure over the next decade. Our colleagues at SURF for the US have a plan for this. And really this plan to expand SURF represents an opportunity to expand US leadership in discovery science across a number of frontiers. So the ask would be to leverage, after the LBNF excavation, to leverage that excavation enterprise to increase underground space at SURF in a timely way and a cost-effective way. So you can see that the cost savings are enough for a small project, something similar to the US Dark Matter New Initiatives, and really being timely. So having this done by the end of this decade is important to compete, for example, for a next generation WIMP search, going deep on that particular science topic. Additional space and facilities for research and development will enable the program, including particle nuclear physics and others like quantum science, technology, R&D, engineering, geology, biology, et cetera. So here we're looking at making SURF a DOE user facility to foster these cross-cutting underground science opportunities in the US. And again, we want to highlight, like many of the frontiers, that we need to invest in the diversity of people and expertise required for the design, installation, integration, and operations of this increasingly complex program. Thank you.
So thank you all very much for the great talks. And now I'm asking the representatives of the Frontier panels to come to the front to join the panel. If there are no questions in the Google Doc, we're going straight to live questions. Please put your hand up.
You've got one online. You've got a raised hand.
I'd like to start with the live audience. First question from the live audience. There's one over there. That's Roger Russo.
So he's one. Sorry. These two.
Hi, this is Roger Rusak, the University of Minnesota. I have one question, which is whenever we do our analyses, we always use the comparison between our data and that we're seeing and the simulations. Behind that is a great infrastructure. And I wanted to know where that infrastructure falls within this enabling technologies. So in particular, one obvious example is Géant. As we develop new detectors, as we go to higher energies and so on, what is the, into which area does the Géant maintenance and other similar tools become? Is it part of the computing or is it within the instrumentation or both?
May I answer the question? Yes. Well, thank you for the question. And many colleagues brought up the current situation of GM4, where it doesn't receive any longer direct support from the US Department of Energy. This is certainly a problem. It belongs to computing, or at least that has been the case in the past. I think that, and according to what we have discussed during the many sessions with small and big experiments, we should have a conversation about how this tool could be supported. And there are other programs that could be contributing, but this is part of a longer conversation.
I'd like to take the next question from the virtual audience. We'll alternate between the two.
Yeah, so should I ask the question or?
Yes.
Yeah, so yeah, I want to ask about how we balance reaching the target versus flexibility. More particularly, how do we make sure our facilities, experiments, and projects evolve with our understanding and time? For example, can we have cavity or room to host some small-scale experiment for future that can greatly enhance the physics opportunities or other opportunities like that? Thanks.
Was that about the underground
The panel
frontier?
would like to take that?
I think all frontier, but just the flexibility and for experiments and facilities, yeah, or theory projects as well, but yeah, or fundings.
So from the underground facilities point of view, I think at this snowmass, we've seen a lot of excitement about some of the largest projects in underground facilities, but also definitely a commitment to keeping room for small and medium scale projects and R&D infrastructure. So we are thinking about all those different size scales as we try to figure out this puzzle.
And this is also happening in Europe and in other places too, because both small and large scale experiments are vital for the future. And indeed, theory is vital for the future as well, Nate. Let's take the next question from the live audience, from the front.
Vladimir Schulze, Fermilab. I have a question for the Instrumentation Frontier, Petra. You indicated that one of your messages or asks is to double the support of detector R&D. And I understand that there is a significant gap between what you want to do and what you have. I don't know, is it in terms of facilities or some technologies are not being properly addressed? Could you please elaborate a little bit what exactly is missing now that we want to cover
Yes.
with this significant increase?
Thanks for the question. So just looking at the DOE, the K-25 money for detector R&D and facilities overall is about 25 million in the US. About a third of that goes to facilities. So that is, for example, the test beams, the silicon facilities at Berkeley, at Fermilab, and so on. And those we need to maintain. We need to keep them up to date because we need to build the detectors for the projects. It's a must. So any reduction that comes into this, out of this program has to go into the R&D part. We cannot touch the facilities part. However, we are still also just scraping by on the facilities side. So there are a lot of improvements needed that we cannot actually afford right now. But any reduction hits the R&D part, and that has been since the last P5 steadily decreased. With inflation, it gets even worse. So I can tell you, for example, at Fermilab, which is one of the biggest programs in this regard, at the last P5, we could still fund something like 20 FTE, technical people, engineers, technicians out of this. Now we are around 8 or so. It's a huge decline, and we cannot really keep up. We are in many areas not really competitive anymore with our European colleagues, for example.
So the next question will take us from the virtual audience. That looks like Fernanda. Go ahead, please.
Thank you. So one thing that came up in actually a handful of the talks, so for anyone or multiple of you who want to contribute to this question, is sure, it needs for some things to be funded, and sometimes things that we had already said that we want to fund, like the core research, apart from projects, etc. And those recommendations, I think, seem very clear. I don't know if the specific part about, say, outreach and education is a specific recommendation to fund. I haven't read the language, hopefully it is. But I think my question is, how much are the recommendations targeting like specific language? Well, one thing is the recommendation to fund this at some level, which, for example, for core research existed as a recommendation in the last process, but there wasn't a recommendation to codify that anyway. So even if it was recommended that some fraction were to core research, the difference between what makes it into specific language and not, do you think it's reasonable or likely that we fall into something similar, or is there language that can be recommended specifically that would help with those cases?
This is a good question for Brice to answer.
Yeah, the last P5 did have guidance on what would be a healthy fraction of our funding for core research. We haven't met that, over the last few years, and so we've tried to address that. It would be good if we would look at that again and reevaluate what we think as a field would be healthy at this stage in our vision. That certainly changed with P5 over the last 8 years, going to more project focused budgets. It is something that Congress is amenable to and they're paying attention to. It was actually, the top priority of our ask in this past year's DC trip for our funding was to support core research. And so we've put that into our advocacy in specific language, but it would be nice for us to think more strongly about that in this P5 report, be a little bit more explicit about that.
Nathaniel, you want to add something?
Great, thanks, Ian. Thanks, by the way, for the great question. So just to add to what Risa said, I think the question of whether these recommendations land and actually are adopted depends in particular, among other things, on the actual language of the P5 charge, how much room there is to advocate for balance between research and projects. And we're in a period here at SNOMAS at the CSS that P5 charge is coming together. So if you feel strongly about this, it's now is a good time to express your enthusiasm for the idea that we should be pursuing balance between research and projects, and that collective enthusiasm hopefully will carry itself into how the P5 process is constituted, and maybe give more room for recommendations in P5 relating to that to have influence.
Okay, so now we're going back to the live audience, Dimitri.
Thank you. Thank you for very nice presentation. The question is to Steve Gorley. So you presented very nice, timely and bold plan for the research and development in accelerators. So how this plan will be coordinated with our international partners?
So sorry, Dimitri, I missed the last part of the question. What are we coordinating with?
So you presented plan for increase in research and development
Yes.
for accelerators. Timely, very nicely presented. How you will coordinate these activities with our international partners who are also involved in many areas of accelerator research and development?
Well, part of the National Collider R&D program is designed to do just that. And we already have models that are working. I mean, the magnet folks have been working with CERN since I started in this field, right? And we have great relationships there, and with Japan and even China as well. The more integrated we become, the easier it is to work with other people because we have a single point of contact, and things are much more coordinated. So I think it's good all the way around. So I see no issues with doing that.
Thank you. I don't see any virtual hands, so we go to the live audience yet again. Who's got one?
Hi, this is
Okay,
Kevin
please go
Pedro.
ahead.
Yeah, this is Kevin Pedro, Fermilab. I wanted to comment on the previous question about the core research budget. I think the answers that were given were good, but we should really emphasize how important this is in the P5 recommendations. I'd actually asked the DOE about this a few years ago because I was curious about, the source of the crunch in core research is that we have 2 huge construction projects going on right now in addition to all this other work. And what I was told by DOE is that in some other parts of Office of Science that they've done a better job at sort of interweaving construction operations research in such a way that nothing gets crunched and they can all be kind of constant over time in terms of how they stagger their projects. So I think we should think really seriously in SNOMAS and the P5 process about having our projects laid out in such a way that we can have that staggering and not have a lot of things happening at the same time, which is what really creates the crunch in core research. And I personally think there are certain proposals that fit that better than others, but there's a lot of details still to work out.
You're giving it to me. Okay.
The other part that also affects the quote core research is the new initiatives, right? Like QI, MI, those types of things that are sort of agency-wide initiatives that all of them are participating in. That's in the research part of the budget. And so, so what we think of as core research is also impacted by those.
Well, can I just say something about the research funding? Vladimir showed in his talk the gradual decline over time of the GARD budget over the last 20 years. That's in absolute numbers. The thing that's hidden in there as well is inflation. And inflation hits the FTEs, right? They cost more every year, assuming people get raises. So that takes a real hit that you can't see. And and he also showed that the directed R&D component has vanished in 2018. The thing that enabled the Hilumi upgrade, was very important. Worked on ILC and Muon Collider. All that's gone now. So we need to and the detector people could say the same thing. It's exactly the same.
And maybe I could add one more thing. So even if the overall budget doesn't go down so much in research for detectors, for example, it gets carved out and specified in more and more ways that our program manager can't actually do much. I mean, his hands are tied. We have now amazing national initiatives with QAS, with microelectronics, AI/ML, which is on the rise, even for use on detector. And those are all great things, but it kind of ties his hands and he can't give us money for certain things that we maybe want to do instead or in addition. Like a lot of the astrophysics instrumentation or instrumentation for neutrinos cannot really be classified as microelectronics, for example. And we are having really a hard time to finance those things.
So next speaker is J. Scott Berg from the virtual audience.
Hello. Brice, in your talk, you mentioned a couple of times faculty buyouts, and that has engendered quite a discussion on the Google Doc, actually, it turns out. So I'm wondering if you'd like to take the opportunity to address the issues mentioned there, such as, getting the institutions themselves to support that, getting explicit support from the NSF, et cetera.
Yeah, so I've looked at the discussion that's been going on in the doc, and so basically to summarize what I've seen there, that's largely been driven by responses from our career pipeline development conveners, is this, that it varies a lot from institution to institution. Some administrations really do not want to take the teachers out of the classroom. Others are, very much supportive. And so it varies a lot whether those buyouts will work at a given institution from one to the next. And I believe that Keith mentioned in that conversation that at NSF, they've sort of typically recently gone away from the idea of trying to do buyouts and, support more funding of undergraduates, coming into the program. But he said that they're looking again at that in the current climate as well.
Yeah, we didn't make any change in any policy. It's always been the policy that individual program directors can sort of run their programs as they wish. And all I was trying to suggest in the Google Doc is that there is renewed attention to this issue because of the desire for broadening participation and enhancing our DEI efforts. In general, to anyone who's considering this, just talk to your program director who would be in charge of the program you would want to submit a proposal to, and they can tell you sort of what the culture is in their program.
Thank you. Let's go to the live audience. Another question, please. One at the front from Marina Artuso.
So I have a question for Petra. I think that the various initiatives proposed by the Instrumentation Frontier are very well posed. And in particular, I strongly support the institution of these R&Ds. Now, in the context of common research and development projects, I was wondering whether you could comment on the importance of creating a platform to share design resources and educational tools with particular attention to the possibility of instituting an instrumentation degree.
You mean specifically tools?
Yeah, so like, for example, in the ASIC design, we were speaking about having a platform for common designs and also for the schools like EDIT and other schools.
Right, yes, absolutely. I mean, we are trying to bring the EDIT school back, for example, to the US, maybe multiple times actually in the near future. But yeah, there's a strong focus also even with our colleagues in Canada to really serve the North American market, because with COVID, there were no schools for a long time. There's a whole pipeline of students and young postdocs that really need to get their hands on some instrumentation. And we're hoping to solve that over the next couple of years with more schools. But for the shared tools, so Farah, I don't know if she's still here, but within the Community Engagement Frontier #1, she had links to industry specifically. And one of her big tries right now is to actually work with industry, with Cadence and so on, for the ASIC licenses, which are a huge burden on our budget because they're very, very expensive. She's trying to work out a model that basically the labs all work together and be treated like one client and thus get a much discounted rate. So I hope this works out, and that would be very favorable for us.
Thank you. Another question is from Anakshi Narayan.
I
thank you.
just one other follow-up on that. I would encourage people to look at the topical group reports for physics education, applications in industry and career, pipeline and development. They all address this topic at some level about ways to enhance instrumentation, industry-focused, technology-focused education in our programs.
Thank you. Meenakshi Narayan, Brown University. I have a comment to make rather than a question to ask, and this comment goes what Ian, what you said towards the end of your talk is, your slide says, to achieve the vision of our field, we must be united in our aspirations, one field with one voice. And I wanted to take this opportunity to say what has emerged since last snowmass is a united community messaging in this last decade, with the support of many, many members of the community engagement frontier who are leading this frontier. And this coherent message year after year to Congress, which is coordinated by US LUAC, US LUAS, SLO, all sorts of users, a committee with various labs, has been really helpful in growing the budget to unprecedented levels in the last decade. And having the community support that with the LBNF June bulge, nobody's knocking at the senator's door. We've come a long way. So I think we should take this snowmass and improving our messaging and also start acknowledging what CEF, members of CFS have done. And we should applaud and thank our community and acknowledge that they have kept an united front, and we've learned how to do it. We will continue to do it. And I also thank the community and the CEF organizers for that.
I think that was very well said. And the last snowmass played an incredible role in that, followed by the P5 that gave us a unity of vision, and people got behind that vision and have done so since 2013. It's been fantastic. But we should keep in mind that it's important to continue that and continue to build on it. Next question is from the live audience again. I think it's the last one. I'm being told we're running out of time. So, okay.
I have a question for Nathaniel, because he's sitting there all by himself, quiet. So you did a good job of explaining how theoretical physics is of utility to this field. And our forward-looking thing is basically graduate students. I'm at a lab, so I'm asking about graduate students at universities. How well are they being supported, particularly in comparison to other fields that might tempt them?
Okay, I guess I should so thanks for the question. How are they being supported? So I think they're being supported as best we can. Sorry, I have to be a little careful in thinking about how I want to answer your question. I think we're very fortunate, of course, in universities that the universities, provide pathways to support students on doing research, theory students, but more broadly research students, also through teaching. So that has allowed us to maintain a healthy and vibrant program. It is certainly the case that we would benefit from more support for students to allow them to contribute, more strongly to their research. And I hope that sort of consideration could be something driving a balance of research and projects. Yeah, I think we have amazing students. We're very fortunate in this field of HEP in its entirety to have extraordinary students, the best students in the world. And to the extent that we can support them and to support them more would be ideal. So thanks.
So thank you very much. As we're now out of time, please join me in thanking all the panelists again.